Welcome to this fall series of the SIAG group on computational geosciences for the year 2023. And today the speaker is Paola Antonietti from Politecnico di Milano. She will give a talk on numerical modeling for earthquake ground motion. But before her seminar, let me give some information about the group on geosciences of SIAM. We have a YouTube channel where you can find all the past seminars. All seminars have been recorded, and you can watch them from there. We also have an Engage. If you are a SIAM member, you can follow us through Engage, and we have, of course, two websites that host the group, where you can find general information about our activities. I will recall the one of you that are not yet a member of SIAM, that you can join SIAM at any time, and in particular, SIAM is very willing to encourage students to participate to the SIAM activity. And indeed, if you have a chapter in your university, the SIAM students chapter are eligible for free membership, free student membership. And this is also true if your institution is an academic member of SIAM. Then you can also, any SIAM regular member can nominate up to 2 students per year for membership to SIAM. So if you have someone who you want to nominate for SIAM membership, you can do it. But there is also news. Now we are also on LinkedIn. So we have opened up our LinkedIn page. So please follow us. You just have to follow the link and just click on the follow-up button. And this is another way with which we want to keep our follower aware of our activities. This year we had the SIAM GS conference. It was a great success. The organization by Jan Norbotten and all the people of University of Bergen was perfect. And here you just find, sorry, I just closed. There is some noise from outside, so I just was saying that it was a great success, and there were some important events. In particular, we were giving the prize to the early career and the career prize winners, Eileen Martin and Christine Schumacher. And also there was a very interesting panel discussing for early career researchers, discussing their perspective both in academia and in industry. Then within the conference, we have 2 interesting events. A visit to an experimental place where they are experimenting CO2 injection, and inside the conference there was this very interesting simulation of CO2 injection. This is an analogical simulation, not a computer simulation, where every day you could see the evolution of this injected fluid that wanted to represent CO2 inside a model of the underground. I remember that we are giving this seminar every second every second Wednesday of the month, apart from December, where we have anticipated by 1 week. And here you have the list of the names of the following webinars. We will announce, of course, through all the channels that we have seen before, the title when it is defined. And so now let's leave the floor to Paola for her talk on numerical modeling of earthquake ground motion. The seminar, as I said, is recorded and posted on the YouTube channel. You can use the question and answer widget of Zoom to pose question, or raise a hand, or answer question at the end. And of course, if you want to say hi to somebody, you can use the chat. Paola, sorry, I've spoken too much. The floor is yours. I will stop sharing, and you can share your PC.
So thanks, Luca. So let me share my screen. Okay, here it is. Can you see me? Can you see the slide? Yes. Okay. So thank you very much, Luca, and to the organizers. I'm really happy and honored to give the first seminar of the autumn session of the web seminar of the SIAM activity group. I already follow the LinkedIn page, so I'm okay from this point of view. What I would like to discuss today is some results and some research line we have been carried out at the Laboratory of Modeling and Scientific Computing concerning modeling the earthquake ground motion. And in particular, I will try to convey the message that this is one of the key steps toward risk analysis. But before entering into the details, so let me first thank the colleagues that are involved in this research. So this is somehow a research project that is strongly interdisciplinary. We do have, of course, mathematicians, and in particular, let me thank Ilario Mazzieri, who is associate professor here at MOX. He's the main father of our computational code that we used to carry out all the simulations I'm going to show you. Let me also thank Michele Botti, who is recently joined MOX through a first Marie Curie fellowship, and now he's a junior researcher. He's an expert on modeling poromechanics. And Stefano Bonetti, a joint doctoral student. And let me also thank the colleagues from the Department of Civil Engineering. They bring their knowledge on earthquake engineering and engineering seismology. And finally, let me thank Marco Stupazzini. He is a former seismic engineer. Now he moved to Munich Re, so the reinsurance company located in Munich, and he always provides us with very research question from the point of view of try to quantify in terms of potential economic losses, the impact of earthquakes. So our research project basically focus and is try to provide some answer and bring a contribution on what is one of the sustainable development goal that the European Union listed some years ago. And in particular, we would like to through numerical simulation and physics-based computer simulation, try to quantify somehow the potential impact of earthquake within, so that can damage human settlements. And this is, of course, towards the development of human settlements that are more safe and resilient to possible hazard, extreme events. And one of these is, of course, the seismic hazard and the seismic risk. In particular, this is a major point in Italy that it's in its whole territory has a very high hazard risk, and the last news in these days unfortunately bring again this topic to attention. So the idea, and this is somehow also the overall flow chart and the outline of the talk, is that to carry out seismic risk analysis, so which ultimate goal is to improve seismic risk protection strategies and policies. There are two main ingredients. On the one hand, what is needed is to be able to predict the expected ground motion that might have a place, might occur after a seismic event. But this is not enough. So you need then to couple on top of that suitable vulnerability models. So given a certain level of shaking of the ground, how this man-made infrastructures will respond. So for today, I will mostly focus on the first part. We do also have a vulnerability, develop some research in terms of vulnerability models and how this can be fully integrated within computational models for earthquake ground motion. But for today, for a reason of time, I will mainly focus on the first part. When you have these two ingredients and you are able to couple them in a suitable way, then you can somehow carry out a fully comprehensive seismic risk analysis. Now, this is this seminar of the activity group on computational geosciences, so I don't have to spend too much words of what is an earthquake in a nutshell. In general, I'm interested in trying to model the ground motion induced by seismic waves, which are a result of an earthquake. And I would like to set up a model that works at the regional scales. So I would like to take into account in my model both far field to near fields responses. As most of you for sure know, so there are two ingredients that takes into account that are very important in the dynamics of earthquakes. So a seismic wave can be always decomposed into primary waves and shear waves. The first one that are also known as compressional waves. So in the solid, the particles in the solid moves along the axis of propagation, or also in the direction of motion. P waves can travel through all type of media, including fluids. On the contrary, shear wave, the motion of the particles in the solid is perpendicular, so it is in the plane that is perpendicular to the direction of wave propagation. Shear waves can propagate through only through solid media, and I'll come back on this in more details later on when I consider more sophisticated models. And shear waves and P waves, compressional waves, are characterized by different seismic wave velocity, which can be which are summarized in the pictures here in the bottom right of the slide, and as a function of in the velocity and the depth. And here you see that on fluid type media, so depth from the surface, shear waves do not propagate. Now, what what is the state of the art? So what kind of models can be employed for predicting ground motion induced by an earthquake? There are basically two different ways of approaching the problems. These are characterized by a increasing complexity of the required input or the required data. On the one hand, you can have empirical models. These are known in the literature like ground motion prediction equations. These are very simple one-dimensional models that somehow gives you, takes an input, the characteristic of the soil at the macro scale, gives you an output average quantities like ground motion, peak ground motion, or peak ground displacement, or spectral displacement. These are very cheap from the computational point of view. They require a quite rough level of data, and as a drawback, gives you back only average quantities or macro scale quantities. On the other hand, we have fully 3D physics-based simulation, so where we set up a differential problem at the macro scale or at a regional level as we are interested in. We solve the full equation. We have then the ground motion time history, and from these results we can recover average quantities. Of course, physics-based numerical models need a very detailed set of data to be set up. But these two approaches are not completely disjoint, and I'll try to motivate why they can be combined together to take somehow the best from the two. So in this graph, what you see is, so as I said before, ground motion predictions equation needs to be calibrated. Okay, to provide reliable answer, there are a number of parameters that need to be calibrated. And this is usually done through historical data. So in this picture, which has been given us by Professor Paolucci, so one of our collaborators, I think that it's somehow explain why both empirical laws and physics-based approaches are very helpful in trying to predict the ground motion. So in this graph, what you can see, so each ballet is a seismic event. Different colors refers to different geographic locations. These are the set of data that has been used to calibrate ground motion prediction equations in the Pan-European region. And the point is that on the x-axis, you see the distance from the recorded data from the hypocenter. On the y-axis, you see the magnitude. Okay, fortunately, there are a lot of events of low magnitude and far with a large distance. This is a good news because this data, so these events most likely didn't produce any important damage. But if you read, if you have a look at the shadow zone, this is exactly the range of potential damage to structures. So larger quakes, we close to the hypocenter. So to make a long story short, if you use this set of data to calibrate an empirical model, it's clear that you have a poor calibration in the near source region, which is exactly the region of interest for potential damage to structures. So on the one hand, one can be still interested in using these empirical models but you can use a physics-based scenario to populate that part of region which fortunately. So let's start with a simple model. So let's first consider one single physics. So supposed to have an elastic medium. This is somehow a simplification. I'll then move towards the end of the talk towards multiphysics wave propagation that are somehow of more interest in this context, but just to give the idea. So the governing equation for an elastic medium, which is the dynamically disturbed, is the classical elastodynamics equation, which looks at this. So here we are looking for the displacement in my domain, which I denote by omega, in the time frame 0 capital T. Rho is the medium density. Then to make the model more realistic, we usually employ, so we take into account that the soil is not elastic, but is more properly viscoelastic. So we have two terms, one proportional to the velocity and one proportional to the displacement itself, weighted for the so-called damping factor, which in practical application is of order 10 to the power minus 2. Let me mention that this is a very, very simple modeling way of modeling viscoelasticities. There are much more complicated and sophisticated models, but for the sake of simplicity, let's consider this model. And we suppose that we take into account the Hooke laws that relates the strain tensor to the stress tensor, and as usually lambda and mu, which are function of the space, denotes the Lamé coefficient. Then in this kind of problem, boundary conditions are always very important. So we suppose to have non-reflecting boundary conditions on the artificial boundary. We create just to delimitate our computational domain. And so a condition like this, where this is a given traction with is zero in practical applications, on the Earth surface. And there are two parameters that are very important, both for the analysis point of view and for the numerical computations, which are related to compressional and shear waves that I discussed before. So I denote the characteristic speed of compressional P waves by Cp, and this is the relation with respect to the Lamé parameters and material density and the shear stress velocity, which is reported here in the bottom right of the slide. Now, for the discretization, what we have started to do a few years ago is try to develop discontinuous Galerkin methods on polygonal and polyhedral grids. We found, which is the general extension and somehow also the natural extension of the classical discontinuous Galerkin method on either tetrahedral or hexahedral grids. So why we found this is useful in this context. So first of all, because of the geometric flexibility. So here we have to take into account different media. Maybe you have structures, and then if you want to incorporate buildings in your computational domain, you have a very full range of characteristic dimension that have to be taken into account. So handling elements that can support arbitrary shape meshes with possible hanging nodes or degenerate faces with respect to the element's diameter in a fully robust theoretical fashion turns out to simplify a lot the process of mesh generation and mesh handling. For example, you can construct a background mesh made of regular hexahedral elements or your favorite elements, and then just chop the elements in order to describe the stratigraphy, the heterogeneity of the media, or any other geometrical feature that is important to incorporate in the model. As a second point, as DG methods, so we can go high order. This is a wave propagation problem, so a hyperbolic problem. So high order is very important to try to minimize numerical dispersion and dissipation errors. We know from the classical DG theory how to make the formulation robust with respect to heterogeneities in the media, and they're naturally prone to massively parallel implementation. So the typical size of this problem is hundreds of millions of degrees of freedom, and we can really take advantage of massively parallel implementation. So the semi-discrete formulation, so the continuous in time based on the polygonal discontinuous Galerkin approximation looks as follows. I have my discrete space for the displacement, which I denoted here by VHA. So this is the space of piecewise polynomials of a given degree, which might vary from one cell to the other. And that's it, without any continuity constraint. So you have piecewise discontinuous polynomials, and my displacement will belong for any time t to this space. The cell, which constitute my mesh partition, can have arbitrary shape. There are some mild geometric regularity requirements for the analysis. But to make an example, we can support elements that have degenerate faces, or elements, so cells where the number of faces blows up in a fully robust way from both the theoretical viewpoint and the computational one. The semi-discrete formulation is reported here in the top of the slide. So you have the second time derivative, the two terms that come from the two pieces for modeling viscoelastic behavior. Then this is the main guy, so the discretization of the elasticity term, which we take in the form of the classical symmetric interior penalty method that goes back to Mary Wheeler and Doug Arnold, where we incorporate, so we take into account the fact that our semi-discrete field can be discontinuous from one mesh cell to the other, and here we penalize the jump of the displacement, so of the trial and test functions. To handle elements of arbitrary shape, these penalty functions has to be carefully chosen in order to make sure that the analysis is robust. This is one possibility. There are even more sophisticated that are more robust to possible geometric degeneration, but I won't discuss them today. And what you can prove that if you set up, if you define a suitable energy norm, which is the classical energy norm that comes from the equation plus a term that penalizes the jumps, because our semi-discrete field is discontinuous from one mesh element to the other, you can prove that the semi-discrete formulation is stable. So for any time t, your semi-discrete solution is bounded in this energy norm by the data. And you can also prove error bounds, provided the exact solution is regular enough. And we prove the error bounds both in terms of the characteristic mesh size of each element and in terms of the polynomial approximation degree. So this is the general estimate, which can be reduced to this one if, for example, the mesh is quasi-uniform and you go for the same polynomial approximation degree in all the mesh cell, and if your solution is sufficiently regular. So from this, bound, which is slightly more easy to be read with respect to the global estimate, so to the localized estimate, what we can conclude is that the scheme provides optimal bounds with respect to the mass size. So the slope is exactly what you would expect, for example, if you go for conforming finite elements. The bounds are slightly suboptimal in P by a factor of 1.5, but this is known in DG methods. So it's not a problem of having a grid of arbitrary shape elements. It's inherited by the DG philosophy. There are ways to recover optimal error estimates in the case of classical grids, which pass through the construction of a continuous interpolant, or if the solution lives in a proper augmented Sobolev space. Now, for time integration, so let me point out that after semi-discretization, you end up with a system of ordinary differential equations of this form. Here, the advantage of using DG methods is that the mass matrix that is in front of the second time derivative is either diagonal, like in spectral element methods, or block diagonal, where each block has the size of the dimension of the polynomials of degree, let's say, pk over the cell k. So in practical application, often the seismic engineers would prefer to go for explicit time stepping, like the leapfrog scheme, because this is very convenient, because all the equations can be somehow either decoupled or solved in parallel. Clearly, the leapfrog scheme is conditionally stable with CFL constraints on delta t, and it's second order, which in many cases might not be the good choice. So if you want to go high order, also in time, we recently proposed for exactly for this equation a space-time DG, or there are many DG time scheme for the wave equations that can be employed also in this case. For example, the original work of Grote and Anna Schnebeli. Now, I'll skip the verification phase. You can you pick up a manufactured solution and check that convergence rates are exactly what predicted by the theory. Let me just show you, for a matter of time, a practical, so a verification test case. A practical example. So this is a simulation carried out trying to reproduce what has been observed during the Athens earthquake of 1999. It was an earthquake of magnitude 6.0. And in this test case, we have, so this our computational domain is a huge block of 30 kilometers depth, and then 45 and roughly 40 kilometers in the two directions. The Acropolis is over here, so you see here little small, and this is the mass of the Acropolis. These are the characteristic compressional, the characteristic velocity of compressional waves and shear waves, as well as the density in the different layers. And on top of that, we have in our discretization model the Parthenon, which is reproduced over here. This is still a simplified model because we were able, due to computational burden, let's put in this way, we were able to simulate up to a maximum frequency of 5 Hertz. But you see, so from these two slides, that the problem is really multi-scale in the characteristic length, because you can go from very huge blocks where then we use high order polynomials to very small cell to capture all the geometric details of the Parthenon. And this is so the distribution of the characteristic mesh size block by block. Sorry, this here is a typo, should be P. This is the polynomial approximation degree. So we go for lowest order elements in the Acropolis area up to polynomials of degree 4 in the bottom slice. And for the Parthenon, we use a characteristic mesh size of 50 centimeters and a polynomial degree, P, sorry, that is 1. And these are some snapshots at 4 different time instants of the magnitude of the computed velocity, which was in agreement with the recorded data from the database. And this is an animation. Let me mention that it has been exaggerated 300 times just for purposes of visualization. So this is just for visualization reasons. And this is the computed absolute value of the displacement. And this is a comparison between the synthetic data at this station, which is reported at this station, which is identified with the identity number 6 on the Athenian schist, and the recorded data. So to be more precise, so the black line is the true datum, and the light gray line is the results obtained with our model, as expected, because there are some simplifications, that there's not a perfect superimposition, but at least the phase and the order of magnitude, so the results match quite well. And okay, I'll skip this. This is another comparison now in terms of the peak ground velocity, but the message is that we are pretty much able to reproduce real data in these test cases. Now, what I've discussed so far, and then in the last 5 minutes, I would like to point out that so up to now we have focused only on one physics. So we've set up the elastodynamics equation, and we solve this equation in the whole computational domain. But this is not always the case, or this is not always the right model in many practical situations. For example, think to an earthquake that took place near coastal environment, and you want also to take into account what happens in the water, or at least you would like to include part of your domain is the sea, or in any practical situations where you not only have an elastic media, but for example, you have a poroelastic media. So it turns out that as a classical discontinuous Galerkin method, their polygonal version is very well suited if you have to attach models where you have different physics. Because since the fields are completely discontinuous, you can embed in the formulation, in a weak sense, the physical transmission conditions. And as I was mentioning, if you want to couple different physics, so I will try to go through, but I don't think to have time to go through all the details. What happens if you have an elastic medium that you want to couple in the model with an acoustic one? So for example, we have elastodynamic in one domain and then acoustic in the other. This is exactly the case where you have so the ground and the sea. Of course, in the sea, you are only interested in acoustic type waves. or you want to study the combined propagation of pressure and elastic media and elastic waves in poroelastic media. This is typically what happens if you want to study the induced seismicity in a geothermal site, or if you want to simulate heterogeneous media with a complex geometry, where in some regions you have really to put a poroelastic model and not the plain, let's say, elastic one. So this is the sketch. So you have a domain where you have a different type of wave propagation phenomena, from acoustic up to elasticity. This is exactly what I discussed so far. And now I would like to show you that if you have different physics on the interfaces, you can take advantage of the DG paradigm to incorporate the physical transmission condition in your formulation. So let's start from a very simple case. Suppose that here we have the elastic, viscoelastic, or in this case, portion of your domain, and then here you have a poroelastic medium. So the elastic equation is this one. This is exactly what I discussed so far. And everything that is in black is related to the red portion of the domain. And the point is that what happens on the boundary. So to discuss, to discretize, to model, the poroelasticity, so to model the poroelastic domain, I go for this model, which has two unknowns, which I denote by UP and WP. These are the solid and filtration displacement, respectively. And then I have the poroelastic stress, sigma, which is somehow the same form as before, but then I have, consistently with the BO theory, this term with this parameter beta, and then I have the poroelastic pressure, which I model in terms of the displacement of the solid and filtration displacement. So I work with the three-field formulation, one which lives in the elastic medium, and the other two that lives in the poroelastic medium. And this is following the BO theory, all the coefficients that are involved in the formulation. So I'll skip all the detail. This is a plain poroelasticity. What I would like to discuss are the transmission conditions and how this can be incorporated in the DG formulation. So you have basically three conditions that the first one relates the elastic displacement with the poroelastic one and the filtration displacement. Then you have a continuity condition at the interface, and then you have your last type of condition. And we propose a formulation which is in terms of this parameter delta that can run from 0 to 1, and according to the value, you can model fluid entries resistance at the interface. And the theoretical analysis we provided is robust with respect to the limit cases delta equal to 0, so this guy disappears, or delta equal to 1, this guy disappears. And the formulation for poroelasticity, this is classical in the DG setting. We have extended to support arbitrarily shaped elements, but this is only, here the complication is technical at the theoretical level. The formulation looks exactly as one would expect. Again, you have to carefully choose the panelization function in order to make sure that the analysis is robust. The point I want to discuss is what happens at the interface. So at the interface, you can incorporate all the information in these bilinear forms that takes into account naturally the three interface conditions I introduced before. in terms of averages and jumps at the interfaces, as in the classical, let's say, DG paradigm. And your semi-discrete formulation at the end reads as follows. So you have, of course, the mass matrix in front of your acceleration term. This comes from the first order time derivative. And here you have all the terms where the E refer to the elastic part, the P refers to the poroelastic, and PE, these are the coupling conditions. Okay. And for time integration, here we can rewrite our problem in this abstract form, and we go for a NUMER beta method to integrate in time. Because here go for leapfrog time integration scheme was, so it's not easy solvable given the algebraic structure of the problem. And okay, I think you can first carry out a verification test. So pick up a manufactured solution, and you can demonstrate, you assess the fact that you obtain the expected convergence rate. What I didn't mention is that for this scheme, you can carry out the full theoretical analysis and recover estimates which are of the same kind I show you in the pure elastic case. And this is what is confirmed by our numerical experiments. We have also tested the case of two-layer medium, so with two different materials, and this is a test taken from the literature, and these are the snapshot of the vertical velocities. In the top row, we don't have damping, so this is the purely elastic case without the viscoelastic term. In the bottom line, we have the damping in terms of the two terms that depends on the displacement, the elastic displacement, and the first time derivative on the velocity. And these are coherent with the results that are can be found in the literature. And now I think I'm running out of time. So you can also, if you are not satisfied, you can also add a third piece, which is the acoustic. And so I'll skip this part. So do the poroelasto acoustic. This is not always enough. There are some kind of applications where you have also to add another field. This is typically when you address the problem of geothermal energy production and the induced seismicity. So in this case, you also need an equation to model the temperature, which lead to the so-called thermoporoelastic equation, TPA, which is the last part of the talk, but I think, Luca, right, I have to go to the conclusions. And to summarize, so what we have worked on in the last years is to extend the classical DG setting, let's put in this way, to model multiphysics wave propagation phenomena, having in mind the prediction of the ground motion induced by earthquakes, but not only, so also induced seismicity due to geothermal energy production, so towards sustainable soil exploitation. The pros we observe is that using general meshes can be very, very helpful in the process of mesh generation and mesh handling, in particular for complicated geometries as those stemming from geophysical applications. So somehow this helps to tame geometric complexity. These methods are robust both from the theoretical point of view and from the practical point of view, to distortions or phase degeneration, or the number of phases can blows up as when you try to do agglomeration to save computational power. And they are naturally oriented as to high order. This is very important for wave propagation problems like their plane DG cousins, and they are fully prone to high, massively parallel implementation. And that's it. So let me thank you for your attention, and let me thank the funds that support this research.
Thank you, Paola, for the interesting talk. It's time for question. You can just raise your hand, or you can, if you prefer to write the question, you can use the question and answer section of the Zoom.
Could I throw in one as they're waiting for audience to wake up? So in the discretization specifically, you had a question, an example for Athens. So what is the level of heterogeneity in the near surface section that you actually have in the model? Like, it's on a piece of limestone, isn't it? Acropolis.
Yes. Yes.
So that being limestone, that limestone is fractured, there must be. So what is the level of detail you have in there?
Okay, so this of course depends on the available data. So in this test case, this is just a picture to give you an idea of the characteristic discretization parameters that are, they come from the stratigraphy. Is just to argument the fact that you can really have a lot of variation, which actually it takes place because if you go from the top to down, the characteristic velocity, I mean, you have heterogeneity, not that much, but this has to be properly taken into account.
Right. But here I see what I think, like top would be maybe soil, and then that soil is meeting a rock. So you have that heterogeneity in there. But do you have any other breaks that might not necessarily be aligned with the mesh?
No, in this model, we didn't take into account specifically the presence of fractures. This would be definitely interested. We have some work also in collaboration with Luca and a former PhD student addressing only the fracture through this, DG paradigm, where in those cases, it turns out to be very convenient from the computational viewpoint to chop the elements, because if they are robust with respect to phase degeneration, this is exactly where you want to chop. So if you have nearly coincident fractures, but definitely fracture should be embedded in, so the present or false of fracture should be embedded in the model, but not in these simulations. These
that
are
could
not
be then, because if I recall, the prediction was a little less in the model than it was in reality in terms of displacement.
Yes.
Same order,
exactly.
So could
Same
that
order,
basically, add a half a centimeter in movement? Because you have a fracture, so things can go up and down.
Definitely.
Okay. There's some questions now.
Urania wants to make a question. Urania Giannopoulos has raised a hand. Sorry. Well, first I read the question on the question and answer.
Okay, now I'm unmuted. Can you hear me now?
Okay. So
I'm sorry. Can I ask or should I wait?
No, ask, please.
Okay. First of all, thank you for this really nice talk. It's really interesting, and I am Greek, so I really remember this earthquake, and I was really surprised to see it, this presentation. I would like to ask if there is if you want to simulate higher frequencies and propagate them in the domain, how does that have a very big load on your computational cost? And or if you can give me some insight on how I can work with higher frequencies in this domain, or if I match different meshes together in a mesh that will be probably be, you know, with the different resolutions around different structures in the domain. I don't know if this is clear.
No, thank you. This is a very, very interesting question. So as I mentioned in the talk, so this simulation have been, so we were able to go up to 5 Hertz. This is far from what seismic engineers would like to see. So they would like to have a minimum of 10 Hertz, ideally go even higher to 100 Hertz. But there are two problems. The first one is the computational burden. So I think if I remember correctly, so this simulation is like 600 millions of degrees of freedom, or even 800 millions. But I mean, this is the order of magnitude to get 5 Hertz. So if you go to 10 or 100, the number of degrees of freedom blows up. But this is not the only or the major problem, let's put in this way. So if you want to go higher order in terms of frequency, so if you want to go to high frequency, which would definitely is what you would like to do and what is needed, you have to have a very detailed description of the underground, of the material properties, because you have to have a much more detailed description of where you have rock, where you have soft soil, and these data are not always available. In particular, this test case is not far from in-depth. This data becomes to be too rough to I mean, to set up a computational grid that can afford higher frequencies. So it's somehow a trade-off. So go as high as possible in terms of frequencies until your data are detailed enough. But from the point of view of the response of structures, even in the case of Parthenon, which is made of rock, 5 Hertz are definitely not enough. I mean, we were able to capture the major frequencies, but we should go definitely much higher. And this is somehow a work in progress.
So you say that the way to overcome the problem is essentially having more information on that geological.
Yeah, from the geologist, this is a requirement. Otherwise, you cannot go with higher frequencies because you won't have a sufficiently detailed geological model. If you have the data, then you have to refine the mesh. I mean, there's always the rule of thumb, right? 5 points per wavelength, more or less. So if you want to go high order, so to go to 5 Hertz, it's like 800 million degrees of freedom. If you want to go 100 Hertz, you have to make the calculation, but the number of degrees of freedom blows up, which means that you have to take into account that your simulations are going to be really, really heavy. But it can be done. I mean, if you have the data, it can be done on, of course, massively parallel computers.
Okay.
By the way, these simulations have been carried out on the Italian supercomputing centers.
Ah, okay, on Cineca.
On Cineca, right? On Cineca, exactly.
Yeah, I'm a postdoc at the University of L'Aquila, so I know more or less.
Okay.
How,
so you know very well earthquake. Since
I mean,
I wasn't there when in 2009, but yeah, it's quite it has made a big impact on the land, on the people. So it's And of course, they studied there also.
I think, well, we do have we have a strict collaboration with L'Aquila, and we do have the simulation also. So the L'Aquila earthquake, I didn't show them for reason of time, but if you are interested, we can of course discuss.
Yeah, I mean, I haven't. Yes, we can.
Sorry, I suggest we exchange your emails and continue the discussion later, because
sure.
we have another question. Then we have.
Yes, I'm sorry for the long dialogue.
It's the email of Paola is written now in the chat.
Okay, thank you very much.
Okay, so you have it. I think it's
Thank you very much.
Simpler. And just the last question from Mohamed Jamin Bou. What's the numerical approach to solve the mathematical model, finite element to finite volume method? Can we use EGA, geometric analysis, to solve the PDE? Okay.
Okay, so the scheme is discontinuous Galerkin methods in their polygonal fashion. I mean, historically, DG comes from the hyperbolic, where they are very much related to finite volumes. So they can naturally support cells of arbitrary shape. In recent years, there has been a huge effort to try to extend the analysis from a classical tetrahedral and hexahedral element to arbitrary shape elements, which are also include degenerate faces or agglomerate type cell. So they are DG to make the answer as short as possible.
Yeah.
As EGA, of course, you can use them as long as you can. Of course, you can go high order. As long as you can afford complicated geometries, why not? I mean, if they are well suited for hyperbolic problems on complicated geometry and they feature low dissipation and dispersion errors, why not? It's worth to try.
Okay, thank you, Paola, for your talk.